So for the final question, we are given the elliptical coordinate system where we have the transformation x is equal to a times the hyperbolic cosine of mu, which I'm just going to call it cosh, times cosine of nu, and then y is a sinh of mu, sine of nu, and z is just equal to z. And this gives the line element a times the square root of sinh squared mu plus sine squared nu, mu hat, plus the same coefficient times nu hat, plus just our z hat. And for the first part, a, we want to find d tau for the coordinate system, so d tau. And we can recall that in general, for any coordinate system, d tau is given by f times d nu, g times d nu, and then we can say h times dz in this case. But essentially what we are finding for d tau is the three individual elements of our space. So if we are looking at some cube in our coordinate system space, you can draw that in here. We're going to have essentially one side which is going to change as f d nu, and the other side which is going to change as g d nu, and the third side will change as h dz if we're thinking that's going backwards in space. So our volume element will be the multiplication of these three individual elements in the three dimensions of our space, and each of the h, g, and f are essentially some scaling factor which has to correspond with how this space changes in that direction. So because we don't necessarily have to have a linear space, given that we're in an elliptical coordinate system, g will be some sort of modification factor applied to d nu, such that we can multiply the three together, and we essentially have some sort of scaled element d mu times f in each of the three directions. So our final d tau is just f times g times h, d mu, d nu, dz. Which in general, if we look at Cartesian, we can say that f, g, and h are all one, d mu is dx, d nu is dy, and dz is dz, and we have just the normal d tau is dx, dy, dz. In this case, however, if we recall again that our area element dl can be broken down into f times mu hat plus g times nu hat plus h times z hat, then right away we can read off from the area element that Jason has given us in the problem, what is our f, what is our g, and what is our h. So of course h is just 1 because we have no factor in front of z hat, and a and g will be the same, and they'll be sinh squared of mu plus sine squared of nu square root, and the same for g. Where I just read these values directly from the line element that he has given you in the problem. Remembering that, of course, because we have our mu hat here, this is f, our nu hat here, this is g, and there's just a 1 here, which is our h. So we can finalize the problem by saying that d tau is f times g times h. So we're going to get an a squared multiplied by sinh squared mu plus sine squared nu d mu d nu dz. A squared sinh squared mu plus sine squared nu d mu d nu dz. Yes, so again, we recall that because we have our coordinate transformation from x, y, and z into our new coordinate system mu, nu, and z, which is the elliptical coordinates, we can have the one-to-one transfers like this. Our line element is just given in the problem as a sinh squared mu plus sine squared nu square root mu hat plus nu hat plus z hat. And we recall the two facts that our d tau, our volume element, is just f times g times h, these three scaling factors multiplied by the three individual displacements or changes in each of the three coordinate directions. And then also we can recall that our line element is given as f mu hat plus g nu hat plus h z hat, where we can then read f, g, and h directly from the line element that is given to us in the problem. And we can find d tau as f times g times h times the three different displacements, which gives us a squared sinh squared mu plus sine squared nu d mu d nu dz. And that's our final volume element for part A. Part B of question 5 says that we want to find the general expression for the gradient of some general field v in our coordinate system mu, nu, and z. So given some sort of general field, v is a function of mu, nu, and z, what is the gradient of this field in this coordinate system? So we recall that in general, for any coordinate system, the gradient is 1 over f dv by d mu, mu hat, plus 1 over g dv by d nu, nu hat, plus 1 over h dv by dz, z hat. Where again, if we remember in Cartesian coordinates, because our f, our g, and our h are all equal to 1, we get the usual gradient of dv by dx, x hat, plus dv by dy, y hat, plus dv by dz, z hat. But in this case, because we're in the mu, the nu, and the z coordinates, and we have a different value for f, g, and h, which we found in part A, we can find the general form for the gradient like this. So we'll substitute in what we know for f. So f is a sin squared mu plus sine squared nu, square rooted, dv by d nu, dv by d mu, mu hat, where of course we just have some general field v, so we don't actually know what this derivative is, we just know that it's the derivative of v respect to mu, 1 over g, which again g is a sin squared of mu plus sine squared of nu, dv by d nu, nu hat, and finally 1 over 1 dv by dz, z hat. So sorry, this is the gradient of v. So our final answer, I'll write it down here, is just the gradient of some general field v in this coordinate system is 1 over a times the square root sin squared mu plus sine squared nu. I can break these derivatives in together and factor it out. So dv by d mu, mu hat, plus dv by d nu, nu hat, plus dv by dz, z hat. And so for some general field v, which is a function of mu, nu, and z in our new coordinate system in the elliptical coordinates, we can find the general gradient of this field v as 1 over f dv by mu, mu hat, plus 1 over g dv by d nu, nu hat, plus 1 over h dv by dz, z hat, where again the h, the g, and the f come from our line element in terms of what is in front of each of the individual unit vectors. And so our general gradient, we can plug all the values in. We don't know what the value of v actually is, so we can just leave it as some field v, and the main thing is getting this constant 1 over a sin squared mu plus sine squared nu, square rooted, plus dv by dz, z hat. And this is the gradient of the vector field in this coordinate system.